Okay, welcome back, students, to section 10.4. Last section, we've made it. Okay, let's get into how to use Laplace transforms that we've been developing in the last two sections to help us solve differential equations. Okay, so theorem. 10.4. So let's type 10.4 is transform of derivatives and solution of initial value problems. Of initial value problems. Okay. Okay, theorem. Okay, suppose that y is of exponential order on 0 to infinity, and that y prime and is piecewise continuous, or just continuous, on 0 to infinity. Period. If the Laplace transform of y is equal to y of s, okay, whatever that Laplace transform of y is, we're going to call y of s, capital Y of s, then L prime or L of y prime exists and is given by L of y prime is equal to S times the inverse Laplace transform of y minus y evaluated at 0. Okay, so in order to do solve a differential equation with a Laplace transform, we need to be given initial conditions. Okay, that's the one stipulation. So what we're doing here is we're taking and we're going to turn something into a Laplace transform, do some algebra with that, and then turn it back into a function using an inverse Laplace transform at the very end. Okay, we're going to inverse Laplace transform this y of s to plug it back into a function of t that will give us our solution to our differential equation. So that's the game plan. Number one, we solve the initial value problem Okay, y prime is equal to t, given that y naught is equal to 1. Okay, so we have L of y prime is equal to L of t. Okay, because y prime is equal to t, so the Laplace transform of y prime should be equal to the Laplace transform of t. Okay, so the Laplace transform of y prime is going to be s y of s minus y of evaluated at 0, or y naught, okay, is equal to, well, L of t. L of t is the Laplace transform of t. And the Laplace transform of t, if we check uh, our table of Laplace transforms, our Laplace transform table, that is just 1 over s squared. Okay. Okay, so now, but what is y at 0? Y valued at 0, that's 1. That's that 1 right there. So this becomes s y of s minus 1 is equal to 1 over s squared. Okay. Okay, let's add that 1 to both sides. We get s y of s is equal to 1 over s squared plus 1. And then I'm going to divide by 1 over 1, divide by s, or multiply by 1 over s. Okay. Y of s is equal to, distribute the 1 over s, and I get 1 over s cubed plus 1 over s. Okay, and so now what do I want to do? Well, I have this as a Laplace transform of y. So if I do the inverse Laplace transform of y of s, I should just get y of t. Okay, or my solution to my differential equation. So inverse Laplace transform of y of s is equal to, okay, inverse Laplace transform of 1 over s cubed plus 1 over s. Okay. Okay, so this is just going to become y of t. Okay, this I can break up into 2 inverse Laplace transforms. This is inverse Laplace transform of 1 over s cubed plus the inverse Laplace transform of 1 over s. Well, I know what the inverse Laplace transform of 1 over s is. We just saw that. That's 1. Okay, so if I check my table of integrals, or my table of Laplace transforms, okay, okay, 1 over s is just 1. So this just becomes plus 1. And the inverse Laplace transform of 1 over s cubed, well, 1 over s cubed ends up being, okay, again, if I think about it as, well, let's go to the table, inverse Laplace transform table, real quick. Okay, and we'll see how can we deal with that 1 over s cubed. Oops. Okay, let's go to our, oops. Laplace table. Working. There we go. It should be at the top here. Okay, if I have t to the n, that becomes n factorial over s to the n plus 1. Okay, well, we have s to the 3, so that's 2 plus 1. So that'd be 2 factorial over 2 plus 1 would be t to the second power. So we have to reconcile that n factorial. And so we could divide by the n factorial to kind of reconcile that. Let me show you how that works. Okay. So if we have 1 over s cubed, then we need to reconcile that we do not have a 2 factorial on top. We would need a 2 factorial on top. So how can I get a 2 factorial on top? Well, I could multiply both top and bottom by 2 factorial. And then that gives me a 2 factorial on top. Okay. And that 1 over s is just 1. The y of t. Okay, and so now I could pull the 1 over 2 factorial, which 2 factorial is just 1/2. If I could pull that 1/2, that 2 factorial on the bottom, I could pull that outside. So that's 1/2 L inverse of inverse Laplace transform of 2 factorial over s cubed plus. So what does this inverse Laplace transform become? It becomes t squared. So this is 1/2 t squared plus 1. Okay. And we could check this really easily because we had a very easy function, y prime equals t. Okay, and if we were to integrate both sides, we would get y equals 1/2 t squared plus c. But they said that y naught was equal to 1. And so if you plug in 0, you would get uh, for t equals 0, you would get 1 to equal c, and so c would be equal to 1. Okay, and so easily checked. Okay, so we don't do Laplace transforms for stuff that we can easily do, ourselves by another method. What we do is we use Laplace transforms for stuff that is hard to do using other methods, and so we're gonna see how we can do that in the next couple of problems. Okay, just start off with an easy one, or relatively easy one, and then we'll get into two more problems that are a little more challenging. Okay, but first, how would we deal with an L of y double prime? Well, that's s squared y of s minus s times y naught. And here, because the y prime, we need 2 initial conditions. That's going to be minus y prime naught. Okay, so we need to know what's the value of the function at 0, and then what's the value of the derivative of the function at 0. So we need 2 initial conditions, and if we want to solve a second order differential equation using this Laplace transform method. Okay, in general, Well, in general, so L of y to the nth derivative is equal to s to the n, y of s, okay, minus s to the n minus 1 power times y naught, okay, minus s to the n minus 2 power times y prime times y prime naught. Okay, so if we had a second order differential equation, we would stop there because that would give me s to the 0 y prime. But if I had, say, a third or a fourth or a fifth, I would just keep going. Okay, minus s to the n minus 3. Okay, y double prime naught minus, and this would go all the way to minus s to the y to the n minus 2 second derivative at 0 minus s, or sorry, no, not minus s, because that would, because the next one would just go to 0. It would be n minus n. Okay. So that would be s to the yeah, s to the n minus n, which is s to the 0 power. So there is no s, but it's just y to the n minus 1th derivative. Okay, evaluated at 0. So that's the general. Okay, that's in general how we do Laplace transform on a function of nth derivative. Okay. Okay. So we're just going to use the first derivative and the second derivative. So let's bring down the first derivative again. What was the first derivative? Y prime is equal to s y of s minus y naught. Okay, and L y double prime is equal to s squared y of s. It's hard to make my capital Y's. Okay, s squared y of s minus s y times y naught minus y prime naught. Okay, so we're going to use those two to do a second order differential equation. Okay, to get the answer to a second order differential equation. Okay, so let's do y solve, okay, using inverse Laplace transforms. Okay, y double prime minus y prime minus 6y is equal to 0. Okay, so this is the homogeneous. Okay, we could use differential operators here, the d. Okay, but let's just do the inverse Laplace transform and see what we get. Okay, so we want the Laplace transform of y double prime minus y prime minus 6y is equal to the Laplace transform of 0. And I do have initial conditions here, which I forgot to put. So y naught is equal to 1, and y prime naught is equal to 2. Okay. Okay, so the inverse Laplace transform of 0 is just 0. Or sorry, the Laplace transform of 0 is 0. Okay, this guy is going to be the Laplace transform of y double prime minus the Laplace transform of y prime minus 6 times the Laplace transform of y, okay, is equal to 0. Okay, so what is the Laplace transform of y double prime? Well, I have it right here. Okay, right here I have, okay, the Laplace transform y double prime right there. So it is just, actually, I'll just copy this right here, this portion of it. Okay, so we can copy that. Copy. Let's bring it down here and see if I can paste it. Okay, yes, that's nice. Okay, so that's L double prime. Okay, minus L prime, maybe I'll just write that because it's only two terms, minus Ly prime, which is S y of S minus y naught. Okay, minus 6 times L of y. Well, what's L of y? Well, that's just y of S. We're calling it the Laplace transform of y of S. So that's y of S is equal to 0. Okay, so what I'd like to do is I'd like to solve for y of S if I can. Let's plug in what we know. Okay, we know that y naught is 1 and y prime naught is 2. So these are 1s. So I get s squared y of S minus 1, or I'm sorry, minus S minus 2. Okay, distribute the negative sign. This becomes minus S y of S. Okay, minus or plus 1. Okay, minus 6 y of S equals 0. Now everything that involves a y of S, I'm going to keep on one side. Everything that doesn't involve y of S, I'm going to move to the other side. Okay, so I get S squared y of S, okay, minus S y of S, minus 6 y of S, okay, and then I'm going to move the plus 1, the negative 2, and the negative S to the other side. So that becomes S. This is plus 2 minus 1, okay, which is just S plus 1. Okay, so I can rewrite that as just S plus 1. Okay, now what I can do is I can factor out the y of S. And so I get S squared minus S minus 6 is equal to S plus 1. And then if I divide by S squared minus S minus 6, I get y of S is equal to S plus 1 over S squared minus S minus 6. And that denominator is factorable. So we have y of S is equal to S plus 1 over S minus 3 times S plus 2. And what I'm going to do here is I'm going to do some partial fractions and then do my inverse Laplace transform. Okay, so let's see what we can get here. S plus 1 over S minus 3 times S plus 2 is equal to A over S minus 3 plus B over S plus 2. Okay. Okay, multiply 3 by S minus 2, oh, sorry, S minus 3, S plus 2. Okay, cancel. Okay, we get S plus 1 is equal to A times S plus 2 plus B times S minus 3. Okay, so to solve for A, we're going to let S equal 3. So we'll get 4 is equal to 5A. which implies that A is equal to 4/5. Okay. And then we're going to let S equal -2. And so when we plug that in, we get -1 is equal to -5b. -5b, which implies that b is equal to 1/5. Okay, so our y of s is equal to, okay, 4/5 times, I'm going to go 1 over s minus 3. You'll see why in a second. Okay, plus 1/5 times 1 over s minus -2. Setting it up to take the inverse Laplace transform. So the inverse Laplace transform of y of s is going to equal the inverse Laplace transform of this 4/5 times 1 over s minus 3 plus 1/5 times 1 over s minus -2. Okay, I could break that up into two Laplace transforms, but basically it's going to become y of t, which is equal to, okay, 4/5 times e to the 3t plus 1/5 e to the -2t. And that's my solution. Okay, why is there no c? Well, there wouldn't be a c. There wouldn't be any constants here. The constants are, 4/5 and 1/5. And why do we get those to be our constants in front? Because we have initial values. This is an initial value problem, so there wouldn't not be any C1s or C2s. Okay, this is a particular solution. Okay. Okay, let's do one more of these. Okay, number 3. Solved. So a lot of partial fraction work involved in these. Solve the initial value problem. Okay, y double prime plus y equals e of t, e to the 2t. Okay, and then we get y naught equals 0 and y prime naught equals 1. Okay, so we're gonna do the Laplace transform of y, y double prime plus y is equal to the Laplace transform of e to the 2t. So we Laplace transform and then we undo the Laplace transform, and that gives us the answer. It's kind of a neat way of working with these things. First we transform and then we undo. Okay, so this is going to be the Laplace transform of y double prime plus the Laplace transform of y is equal to the Laplace transform of e to the 2t. Okay, well, what was the Laplace transform of y double prime again? Well, that's a little earlier on in the notes. Okay, but it was just s squared y of s, okay, minus s y naught minus y prime naught, right? Okay, so that was L of y double prime. Well, what's L of y? Well, that's just y of s. Okay, that's the definition of y of s, is the Laplace transform of y. And then that's gonna be equal to the, well, what's the Laplace transform of e to the 2t? Well, that's 1 over s minus 2. Okay. So from that table of Laplace transforms, okay, we can see that the exponential here, number 2, is e to the at is 1 over s minus a. Okay, so we can go forwards and backwards. Okay, okay, so this is going to become, well, y naught is 0, so this whole thing goes to 0. Okay, and y prime naught is 1. So this becomes s squared y of s. Okay, this is 1 minus 1 plus y of s is equal to 1 over s minus 2. Okay, so let's add 1 to both sides. This is 1 over s minus 2. Oops. Okay, plus 1. Okay, this is going to be s squared y of s plus y of s is equal to 1 over s minus 2 plus 1. Okay. Okay, factor out a y of s, and I get y of s is times s squared plus 1, okay, is equal to, let's get a common denominator here. This is 1 over s minus 2 plus s minus 2 over s minus 2. So this becomes s minus 1 over s minus 2. Okay. So this is y of s times s squared plus 1 equals s minus 1 over s minus 2. S minus 2. Okay, and I'm going to divide by that s squared plus 1. Okay, so multiply by 1 over s squared plus 1. Okay, and so y of s is equal to s minus 1 over s minus 2 times s squared plus 1. Let me put the s squared plus 1 first. Times s minus 2. Okay. Okay, and then once again, we're going to use partial fractions on this. Okay, and so I get s minus 1 is equal to, now the denominator here is s squared plus 1. Okay, and so I have to take into account that when I do partial fractions, it has to be 1 power less. So if I have a quadratic, I have to have a linear. So this would be as plus b plus c over s minus 2. The 1 degree less than a linear is a constant. Okay, 1 degree smaller than a quadratic is a linear, but I have to take into account that the linear could have included another constant. Okay, so it has to be as plus. Okay, let's multiply through. Oh, sorry, this is s squared plus 1 times s minus 1. Okay, let's multiply through. Okay, by s squared plus 1 and s minus 1. Now, I'm not going to be able to use the trick that we did before because I have a quadratic here, so I'm going to have to use some algebra. Trick that we did before was when we let a or b or c equal to something, and then I could get rid of it. I can use that on c, but I can't use that for a or b. Okay, so s squared plus 1 times s minus 1. Oh, you know what? This is s minus 2. I'm sorry. S minus 2. Okay, s squared plus 1 times s minus 2. Cancel, cancel. We're left with s minus 1. Okay, is equal to a s plus b times s minus 2 plus c times s squared plus 1. Okay, so I can zero out as plus b if I let s equal 2. Okay, then I can get this whole thing to be 0. Okay, and so I would get negative 2 minus 1, which is just 1, right? So 2 minus 1 on one side is equal to 0 plus 2 squared plus 1, that's 5. Okay, so that's going to be c times 2 squared plus 1. So this is 1 is equal to 5c. So c is equal to 1/5. Okay, we got c, but because s squared plus 1, whenever I plug anything in, it's just going to give me a positive value. It's not going to go to 0. Even if I plug in 0, it doesn't go to 0. So I know what c is. Let me just circle that. Okay, so c is 1/5. But let's go back to this equation. This guy here. Okay, and I have s minus 1 is equal to as plus b times s minus 2 plus c times s squared plus 1. I'm going to multiply this out. Okay, I'm also going to write the left side as 0 s squareds plus 1 s1s minus 1. Okay, 1s minus 1. This equals, okay, distribute. I'm going to get a s squared, okay, minus 2as distribute b plus bs, okay, minus 2b, okay, plus c. Well, we know what c is. C is 1/5, so maybe we'll just plug that in. So distribute 1/5, I get 1/5 s squared plus 1/5. Okay, okay, good. Okay, so what I'd like to do is I'd like to get all the terms together. So I'm gonna group the terms together. I'm gonna say that a times s squared plus 1/5 times s squared. Okay, group that together. Okay, the s terms I'm gonna group together. That's gonna be negative 2a plus b. Oops, sorry, negative 2as plus bs. as plus bs. Okay, maybe I'll put a plus there and group those together. Okay, and then I want to group the constant terms together. So that's just going to be negative 2b and 1/5. That's negative 2b, okay, and 1/5. Okay, and then I'm going to set that equal to 0 s squared plus 1s minus 1. I'm going to solve for a and b by looking at the like terms. Okay, if I factor out an s squared, I would get a plus 1/5 times s squared plus factor out an s, that would be b minus 2a, okay, s, and then plus, and then this would just be 1/5 minus 2b. Okay, and we can see that that corresponds to 0s squared 1s minus 1. Okay, maybe I'll put a plus and negative 1. Okay, but now we can see that these correspond directly to those expressions. So I know that a plus 1/5 has to equal 0. Okay, so a plus 1/5 has to equal 0. Well, that tells me that a is equal to negative 1/5. Okay, and then I can use the last term here. 1/5 minus 2b is equal to negative 1. Okay, that I can use the constant term to solve for b. So this is going to be minus 1/5 minus 1/5. That's going to be negative 6/5. Okay, so I've got negative 2b is equal to negative 6/5. If I multiply by negative 1/2, that just becomes 3/5. So b is equal to 3/5. Okay, so a was equal to negative 1/5, b was equal to 3/5, and c was equal to positive 1/5. Okay. Okay, so now we have a, b, and c. So that told me that y of s is equal to, okay, a, which is negative 1/5 s. Oops, sorry about that. Negative 1/5 s plus 3/5 over s squared plus 1 plus 1/5 over s minus 2. Okay, so now I just have to kind of clean this up. Okay, and so I'm going to break this apart. Okay, hopefully you understand the algebra that I'm doing here. Okay, so y of s is equal to, I'm going to break this apart, this negative 1/5 s and 3/5. Okay, break that apart. Well, maybe I won't skip steps. Just go negative 1/5 s over s squared plus 1. Okay, plus 3/5 over s squared plus 1. Plus 1/5, I'm going to write this as 1/5 times 1 over s minus 2. I'm just trying to set this up for my inverse Laplace transform. Right? Okay, so this is going to become negative 1/5 times s over s squared plus 1 squared. I'm going to write it like that. Okay, plus 3/5 times 1 over s squared plus 1 squared plus 1/5 times 1 over s minus 2. Okay. Okay, y over s. And now I want to inverse Laplace transform this thing. Okay. Well, this is going to become the inverse Laplace transform of that is the inverse Laplace transform of each of these three. And they do correspond nicely, okay, to sines and cosines and exponentials. Okay, so the inverse Laplace transform of s over s squared plus 1 squared is just, you know, the b in this case, b squared, right, is cosine bt. This is cosine. Okay, cosine t. Okay, this guy here is b over s squared plus b squared, which is sine t. Okay, and then this guy here, 1 over s minus 2, well, that's just e to the 2t. Okay, when I inverse Laplace transform those guys. That's why I kind of set it up the way that I did. So the inverse Laplace transform of negative 1/5 times s over s squared plus 1, okay, plus 3/5 times 1 over s squared plus 1 squared, that should be a 1 squared, okay, plus 1/5 over 1 over s minus 2, okay, so hopefully you can see kind of where we're going and kind of what the answer is going to be. Okay, so this is y of t is equal to the inverse Laplace transform, or negative 1/5, the inverse Laplace transform of s over s squared plus 1 squared, plus 3/5 times the inverse Laplace transform of 1 over s squared plus 1 squared, plus 1/5 times the inverse Laplace transform of 1 over s minus 2, okay, and so y of t is equal to negative 1/5 times the cosine of t, okay, plus 3/5 times the sine of t, plus 1/5 e to the 2t. And that should be it. Okay, and that's 10.4, and yeah, that's the end of chapter 10. So I will not see you in the next video because there is no next video. So good luck on your last exam. Okay. Okay, see you later.